This video introduces the efficient training of instance segmentation models, with a focus on labeling rules and model training. The overall process consists of 6 steps: data collection, data processing, data labeling, model training, model validation, and model export. Data collection lays the groundwork for labeling. It ensures that the acquired images are clear and complete. In addition, the dataset must be sufficiently large and diverse to support effective training. The other 5 steps form the complete training workflow, performed in Mech-DLK. For detailed instructions, refer to the introductory video on instance segmentation model training. This case focuses on loading irregular sheet metal parts. The project goal is to pick randomly stacked parts from a bin. To support this, instance segmentation with Mech-DLK is applied to recognize the topmost exposed parts, enabling layer-by-layer picking until the bin is empty. Now, let's go through the specific process. The first step is data collection, which is the preparatory work. During image acquisition, adjust the 2D exposure mode and white balance settings to improve image quality based on project requirements. In addition, manually reposition workpieces to ensure data diversity. After collection, select only high-quality images for labeling and training. Please refer to our documentation for details. Next, proceed to the data processing. Open Mech-DLK. Create a new project. Select the Save path. After entering the project interface, add the Instance Segmentation module. Then, import the image data. Here, select Import folder. This folder contains the previously selected high-quality data. Next, set the ROI to exclude irrelevant background and reduce 2D image scaling, avoiding feature compression. When setting, ensure all target objects are fully contained within the ROI across all images. Note that the ROI set here will be automatically applied during the subsequent model application. Therefore, set an appropriately sized ROI to prevent targets from falling outside the region if the bin position shifts. Use the keyboard's down arrow key to quickly cycle through images and verify all targets remain within the ROI. After this, create classes. In the Classes panel, click the Add New button to create classes based on the object type or feature. For this scenario, only one type of workpiece needs to be recognized, with no need to distinguish front from back or other specific features. Thus, a single class is sufficient. The class name can be set as needed. Next, let's proceed with data labeling. Based on the project requirements, establish unified labeling rules. In this scenario, only the topmost exposed workpieces need to be labeled. The picking center and other parts of the workpiece should not be heavily occluded, and the pick point should not be too close to the bin wall. Given the complex shape of the workpieces, it's recommended to use the polygon tool to outline each object by adding anchor points. Labeling should closely follow object edges to ensure accuracy and avoid omissions or errors. Due to the large dataset, label only a representative subset initially. Select images with distinct positional or shape variations to maximize diversity. Now, 10 labeled images are available for initial training. Move all labeled data to the training set. Then, split the data into training and validation sets. A typical split is 80% for training and 20% for validation. Move on to model training. Configure the training parameters based on actual project requirements. Ensure that the adjustments in data augmentation parameters don't affect workpiece features. Brightness adjusts the overall lightness or darkness of the image. As the lighting during data acquisition can't cover all conditions throughout the day, the brightness range should be extended to improve model adaptability. In this case, the lighting was relatively appropriate, so adjust the brightness as needed to improve data stability and performance under varying lighting conditions. Contrast controls the difference in gray levels within the image. Since the color difference between the workpieces and background is minimal in this scenario, increasing contrast can make features more distinguishable. Just use the default settings here. Next, adjust the parameters related to object pose, including translation, rotation, and flip. Translation moves the entire image horizontally or vertically by a certain distance. Rotation means turning the image around a specific point by a set angle. Flip refers to flipping the image horizontally or vertically by 180 degrees. In this scenario, top layer workpieces in the bin are randomly stacked. Even similarly exposed parts may vary in position, orientation, or flip. Thus, adjust these parameters appropriately to retain key features and ensure the model recognizes all symmetrical and varied poses. Scale adjusts the image size proportionally. Given the presence of similarly sized workpieces in this scenario, adjust the parameter as needed. Then, configure the training parameters. Input image size refers to the pixel-wise height and width of the image input to the neural network for training. The larger the image size, the higher the model accuracy, but the lower the training speed. To speed up training, the image size should be as small as possible, provided that labels and part details remain clearly visible. The default value is sufficient for this scenario. Epochs refers to the total number of training iterations for the model. In this case, the image features are relatively complex, so the number of training epochs should be increased. Other parameter values can remain at their defaults. Since model fine-tuning is not involved in this scenario, leave it as default. Click OK to save the parameter settings. Once configuration is complete, start the training. The show chart function can be used to monitor the accuracy curve. Combine this with the accuracy values to determine whether the results meet the required precision. Training has now completed all scheduled epochs. As shown, accuracy has stabilized and loss is low, which meets the requirements. After the training is completed, evaluate the model performance by combining validation results with segmentation outputs. Use both validation statistics and visualized masks to check for any missed or incorrect detections. Start with the training and validation sets. As shown, both sets currently demonstrate good recognition performance. Then check the test set, which evaluates the model's generalization and requires close attention. If missed detections are found, additional labeling is required. Note that the entire image should be labeled, including both detected and missed instances. After that, add the image to the training set for retraining and validation. To address incorrect detections, post-processing is commonly used by setting a confidence threshold during model application. This helps filter segmentation results. After reviewing the current test set, the segmentation results are generally accurate. One image was found to contain incorrect detections, and 2 additional images had missed detections. Thus, supplement the labels for missed detections. Labels can be added in small batches through repeated iterations until all detection results are satisfactory and the model performs well. After labeling, add the 2 missed detection images to the training set. Ensure the ratio between the training and validation sets remains within an acceptable range. Then, retrain the model. When finished, validate and check the data as before. Currently, validation is complete. Check the segmentation results again. The model's instance segmentation performance in this scenario meets the requirements. Thus, export the trained model. This concludes the efficient training process of the instance segmentation model. After exporting the model, it can be used in Mech-Vision for object recognition and localization. For guidance on how to use the model, please refer to the next video application of instance segmentation models. You can also refer to our documentation for more details about training instance segmentation models.